Okay. Right. This question says some stuff about electric hob. Um, it says when all four heating elements are switched on, the hob draws a current of 26 amps from the 230 volts main electricity supply. Calculate the resistance of one heating element when the hob is switched on at full power. So one heating element, if there's four of them that have a current of 26, then one of them must have 26 divided by 4. So what we need to do first is divide this current by 4 to get 6.5 amps. And then it says calculate the resistance of one heating element. The formula you need is that resistance is voltage over current. The voltage from this question is 230. The current that you use is not the 26 because it's only for one heating element. You do that divided by the 6.5, and you should get the answer, which is about 35. And that would be that. So just be careful of reading the question carefully when you do that kind of thing. Oh, two significant figures as well. So my calculator said 35 point something. So it just wanted 35 as the answer. The table gives the maximum current that can safely pass through copper wires of different cross-sectional area. Okay, so it says if a wire has this area, then the maximum current is 11.5. As the area gets bigger, it seems that the maximum safe current gets bigger. The power sockets in a home are wired to the mains electricity supply using cables containing 2.5 millimeter squared copper wires. So these ones. Most electrical appliances are connected to the mains electricity by plugging them into a standard power socket. It would not be safe to connect the electric cooker hub to the mains electricity supply by plugging it into a standard power socket. So, to answer this question, you need to say that the at this area, at 2.5 millimeter squared area, the maximum safe current is 20 amps. And if we just go back to the cooker hob, it said that when all four are switched on, it can draw a current of 26 amps. 26 amps is more than 20 amps. So you need to explain that for that thing, the maximum current of the hob exceeds 20 amps, or is more than 20 amps. There's only 2 marks, so is there anything else we need to say? Yes. So when you have too much current flowing through a wire, essentially it can overheat or melt the wire. Okay, so the wire might overheat or melt. You probably just need those 2 points really to be able to get that. Again, just in case anybody has joined about the in year 11 that are here for the physics thing, even though I am doing some physics right now, I'm just going through the homework that the others had. From 8 o'clock, I will be doing for the full physics topics from scratch, including energy, electricity, particle model of matter, and atomic structure. So if you want to come back at 8 o'clock, but you're welcome to stay. Feel free. Mains electricity is an alternating current supply, battery supply direct current. What is the difference between alternating and direct current? I mean, it's sort of in the name, really, but you want to say that alternating current um, changes direction or constantly changes direction. It alternates. Whereas a direct current flows in one direction only. Okay. I got some more questions here. Um, this should have been the homework that was given to the year 10 students this week, the one I'm doing right now. But once again, and I don't know who that is that's asked that question. Um, so yes, just a reminder if anybody else has just joined from year 11 that I'll be doing the full physics stuff from 8 o'clock. This is just me going through some homework that some people had. Um, um, None of these questions that I'm looking at right now are specific to higher level. I mean, I don't see anything here that I would say is higher level, just to be clear, if anybody's worried about it. I think these are all fair game either way. Figure 1 shows a circuit diagram. So you got the 4, 5, and 6, didn't you? Circuit diagram containing two identical lamps arranged in parallel. The reading on the ammeter is 186 MA. This is a little bit annoying because milliamps are 1,000 times smaller than an amp. So actually what this is 0.186 amps. If you divide it by 1,000. And then what do they want? Which statement about the current through the lamps is true? Now, because these are identical lamps, they will basically, and it's a parallel circuit. This is important. There's a parallel circuit here. In a parallel circuit, and I'll be going to do this in more detail later, but in a parallel circuit, the current gets split along the branches. Okay, and it's split based on what you have on the branch. So if we have two identical things, then the current is evenly split across the branches. So when it says which statement about the current is true, then the current through both of them will be half of the current showing on this reading, because it'll split two ways essentially. So if you do 0.186 divided by 2, you'll get 0.093, and that is the current through both of them. Okay, because that 0.186 is split, and you have to convert the milliamps to amps there. One of the lamps breaks and is not replaced. Which statement about the current in the other lamp is true? Now, if one of them breaks, then what happens, and this is a bit of a technical thing, but what happens is that essentially we get rid of, so let's say which one broke. Does it say which one broke? It doesn't, it's not replaced. So one of them is broken, which means that almost doesn't exist now. Now, what that does is it doesn't change the current going through this one, because what happens is it decreases the current overall in the circuit. When you have an extra wire, it increases the current in the parallel circuit. But now that's not there, it means it decreases the current in the parallel circuit. So now, previously we had 0.093 here and 0.093 here. This is gone. This just stays the same. So it is still just 0.093 amp through the other one, because it's not that it gets the rest of the current, it's gone now, and the overall current in the circuit decreases. Figure 2 shows a circuit that can be used to alter the brightness of a lamp. This is a variable resistor. The resistance of the variable resistor is increased. What effect will this have on the brightness of the lamp? Resistance and current are essentially opposites of one another. Right, yeah, so let me answer this last question. Everything I'm doing right now is related to the physics exam tomorrow. However, I am at the moment just going through what was on some homework that some of the other students got this week. It coincidentally happens to be the same as what is on the exam tomorrow. But in terms of what I'm, from 8 o'clock, I am doing a full recap of what is on the exam tomorrow. It is just, yeah, this stuff is relevant, but it is just homework questions. So what we need to understand about resistance is that resistance, as is in the word, essentially, it resists current, so it slows down current. So the bigger the resistance is, the less the current gets. So if I said that the resistance is increased, how does this affect the brightness, and explain it? Well, you need to first say that when you increase resistance, the current decreases. Put these in words. So that's the first thing you need to explain. And when you decrease the current going through a bulb, it makes it dimmer or less bright. That's it. So you increasing it almost acts like a dimmer switch, okay, where you can, and that literally is what a dimmer switch does, by the way, but separate. Write down this equation. The equation is V equals IR, any formula of that. So V, voltage is current times resistance. And then they're going to ask you to calculate resistance. If you rearrange this equation, resistance is voltage over current. The voltage in the question they told you is 3.3. The current is 0.15. The one thing I will stress when I do my thing later is that with any physics question, especially in exams, really look at all of the units, because that is where they try and trip you up. Okay, the units are very important to check to make sure you're using the right units in the question. In this case, it's fine because they're in volts and amps, which we wanted. If it had been like milliamps or kilovolts or something like that, you would need to do some conversion first. 3.3 divided by 0.15 is 22, according to the answer that I'm looking at. Sketch a current potential graph for a filament lamp. Again, one of the things that I'm going to be saying later is that there are only two of these graphs that you in theory need to know. The one for a lamp, which is like, it goes, well, it goes like that here, but it also, if there was a negative, it goes into the negative, but that's it. And the other one that you need to know is for a diode, which goes kind of like that. But yeah, that's what the graph is for a filament lamp. Do you have to explain it? No, you don't. I'm not going to. And the next question is exactly the same, basically. What is the name of the component whose IV graph looks like this? It is a filament bulb lamp. Same thing. Have I done? No, 6 as well. And then we have a circuit containing a 6-volt battery. What is the potential difference across X? One of the most basic things to know in electricity is that in a parallel circuit, which is what this is, even though it looks like a slightly weird parallel circuit, it is a parallel circuit. The voltage or potential difference, same thing, across any one branch is always the same as what we get from the battery. It's always the full amount. It's not shared or reduced or anything. Everything gets 6 volts. So when it says what is the potential difference or voltage across X, it is 6 volts because that's what comes from the battery. It is the same number every time. And then it's what's the resistance of X. Well, that should be easy as well because we have 2 bits of information about X. We have the current and the voltage. Resistance is voltage divided by current. Voltage is 6, current is 2. 6 divided by 2 gives me 3 ohms of resistance. And lastly, what is the current in Y? Again, a very important aspect of a parallel circuit, as I showed you earlier actually, is that the current that we're getting gets split. So that 3 amps that we're getting here gets split. 2 went that way, and that means 1 must have gone that way. So that 3 has split into 2 and 1. So the answer to that question is 1. And then they want the resistance of Y. Resistance of Y now, again, resistance is voltage over current. The voltage is 6 because it's the same. Current we just worked out is 1. 6 divided by 1 is 6. And then, right, then it says when the temperature of resistor X increases, its resistance decreases. What happens to the potential difference? Well, firstly, potential difference, remember, in a parallel circuit is always the same. It stays at 6 volts all the time. So that is that. What happens to the current in X? Well, if you increase the resistance, the current decreases. They're like opposites of each other. So the current decreases. And then the total current in the circuit also decreases. Because now, remember, if that had gone down, let's say that's gone down to 1 for some reason, okay, then that 1 and 1 is now the total current, and this would be 2. So the total current in the circuit also decreases. So that would be that. And that covers questions 4, 5, and 6, which and nobody has asked any other homework questions, which is why I'm going to now move on to the other 2 questions that people have asked, which is all maths related. Trig graph values, like the rules where you do opposite or expect on the brackets. Okay, there's 2 slightly different questions there, but I will do that. And then I'll do a couple of loci examples as well. Weird loci. I'll find something. Right. There's a slight confusion in this question, which says trig graph values, like the rules where you do opposite or expect. They're 2 different things there that you've asked. But this that I'm about to draw is a graph of y equals sine x. Okay. Now the graph of sine goes up to 1 on that bit and down to -1 on that bit. And then it has intervals of 90 at every one of these sort of bits where it sort of changes direction or reaches an axis. So it's 90, 180, 270, 360, 50 and so on. And I'm just going to illustrate this on my calculator as well. So remember, a graph or an equation of a graph, as I've said before, is just like a machine that tells you what the y coordinate is at any x coordinate. Now, if I take this coordinate right there, the x coordinate here is 90. The y coordinate is 1, right? And if I type in sine 90 into my calculator, let's make sure I'm in the right mode, sine 90 into my calculator, it will tell me that y is 1 when x is 90. And that's why that is like that. If I type in sine 180, what should it tell me? Well, at 180, what's the y coordinate? It is 0, and it should tell me that. If I type in sine 270, it should tell me it's -1, and it does, because 270 is there, and the y coordinate is -1 there. So that's why the sine graph looks like this, because the calculator sort of tells you it looks like this, which means you could, in theory, use the calculator to figure this out, essentially. You could use the calculator to draw the graph if you had to. Now, I think the question that has actually been asked is the transformations of these curves, because that's really what happened at GCSE. So, for example, if I've got the graph of y equals sine x, I'm going to bring this down a little bit. And I now said to you, draw the graph of y equals 2 sine x. Well, what 2 sine x does is when you have a number being multiplied by the outside of a function, being multiplied by it, then what that does is it only affects the y coordinates. Anything outside, that's the way I think of it, outside as in there or at the end, affects the y coordinates. Anything inside, if you imagine that's where the brackets are, that's affecting this x, affects the x coordinates. So this is only going to affect the y coordinates. And what that does is it multiplies all your y coordinates on the graph by 2. So what will that look like? Okay. It means that this coordinate that we said here that was at 91 will now be at, if I times the y coordinate by 2, at 92. This coordinate will stay where it is because if the y coordinate is 0 and you times it by 2, it doesn't change. So all of these ones won't move because the y coordinate is 0, and 0 times anything is 0. But all of these other troughs and peaks will effectively be sort of stretched downwards a little bit. So that will go to there, and that will go to there, and that will go up to there. And which means that the new graph of y equals sine 2x, that bit badly, ends up looking something like that, as if you grabbed it and stretched it upwards. Okay. That's what happens when you put a number on the outside of a any function. It basically multiplies your y coordinates by 2, which means it feels like the graph is like stretching as if you're picking it up and stretching it up and down. And that's what we have just done there. If I just go to the other extreme of this, cross all that out, and say, what would happen if I had instead put that 2 there? Okay, so it would be y sine 2x rather than 2 at the front. What that does is it only affects the x coordinates, like I said. So when it's inside the brackets like that, it affects the x coordinates, or when it's just affecting the x. If it's outside, it affects the y coordinates. Now, however, when you do anything to the x coordinates, as we're about to do, you do the opposite of what you think you're going to do. So you think that I've times by 2 here, and you times the x coordinates by 2. You don't. You actually divide the x coordinates by 2. So what actually happens then is, if we just take one point at a time, like that one, that is 91, isn't it? That's the coordinates, 91. Now, if I divide the x coordinate by 2 here, it becomes 45, 1. So this will effectively sort of move to the left slightly and be there. This 180 coordinate will also halve to here. This 270 will halve to 135, which will be here. The 360 will halve to 180, which will be here, which means that you end up with something looking like this. Whoops, again. Where effectively the graph has sort of been squashed inwards. You see what I mean? They're all closer together than they were. It's like a wave with a shorter wavelength. And that's what has ended up happening there to that particular graph. If we wanted it to have gone sort of wider, then think about what we did. Well, we times by 2, and that caused it to sort of come in a bit. We would have needed to divide by 2 to do the opposite, which would have meant, so if you wanted to have it wider, it would have been something like sine a half of x, or x divided by 2. That actually stretches it outwards. So it is quite a complicated point to it, but that is really it. I mean, they're the two complicated bits. The easier bits of that, which I actually missed, is when you just add something to the end of a function. So if I had said like sine x plus 2, then all that would have done is would have taken my graph, which I don't have now, but moved it up 2 units. So it would have been like the same graph, but just higher. So it'd have been like up here somewhere instead. That what a plus would have done to the end of it. A plus inside the brackets would have moved it left and right, but again, the opposite way to what you think. So a plus 90 actually moves it left 90. So imagine you're picking it up and you're moving it all to the left a couple of, or 90 units in that particular case. So I think that's what you were asking, but we can obviously do more of that if you wanted to ask it in the lesson, especially since we're doing maths next week as well. Right, I'm going to just finish off with having a look at some examples of loci, given that there's no other specific questions, and then I will return at 8. So see if I can just find something on loci. Yeah, I should be able to do more of that on Sunday. That's fine. We do, as I say, for people in year 10 and stuff like that. As I say, some of these topics we do in year 11, basically. So we have a full thing on graph transformations and a lesson that we do with all the maths when we do one of our math lessons. These are deliberately put into the later part of the syllabus. Loci and construction. Okay. Okay, just a couple of examples quickly. I'm just going to do that. I can just immediately find. A common question in loci and construction is something called an angle bisector, which, I mean, the word bisector, but to bisect something basically means you sort of split it in half. So if you have to draw an angle bisector, there's an angle here, and I need a line that basically splits that in half. That's what I need. But I can't just do it by measuring, which would have been the logical thing to do. I could just measure it with a protractor and halve it. That would be a sensible thing to do. But this is not a sensible topic. What you have to do is use only a ruler and compasses. In this case, only a compass is all that's actually needed. This is what you do. And again, it just takes a bit of practice with these questions. You get your compass, and again, it's very hard to show you this online, but get your compass, open it up a little bit, right? Put the sharp bit there, and obviously have a pencil inside it. And then draw, keeping it the same distance, draw an arc there, and then you'll have another one here as well. So draw 2 arcs on these lines. Then you put your sharp bit here, and you can at this point widen it a little bit more if you want. As long as you, when you do it, the next 2 times you do this, it stays the same distance. Put your sharp bit there, and then draw another arc, and it will be like here somewhere. Okay. And then put your sharp bit there and draw another arc with it, and it'll be like here somewhere. It'll look like that. And when you're doing these in an exam, they are looking for these arcs. That's exactly what they're after. And then all you do is you get a ruler and you draw a line from where we started through to where these arcs have crossed. And that would be an angle bisector of that particular angle. And then I will do one more question, which is more of a exam style question. Which is here. Now, I'll try and explain a couple of the only other loci, all of the loci things basically in this question. But A, B, and C has 3 points on a map. 1 centimeter is 100 meters. P is 300 meters from A. Okay, now 300 meters means 3 centimeters on your scale. If you're trying to go, okay, if you imagine you're standing exactly where you are and you needed to create an area 2 meters around you that nobody could enter, nobody could get 2 meters within 2 meters of you, then if you think about what that would look like, it would be a circle around you that's 2 meters, that has a 2 meter radius, right? If you're here and you want nobody to come within 2 meters of you, then you need a circle that's 2 meters away from you that has a radius of 2 meters. And then if I could draw properly, that would be more accurate. But yeah, you get the idea, right? That would cover an area of 2 meters from you that nobody could get to, right? Because anywhere inside the circle is less than 2 meters from you. So they have to stay outside the circle effectively. And that's what the first bit of this question wants you to do. It said if there's a point P that is 300 meters or 3 centimeters away from A, how do you get space that's 3 centimeters from A? Well, you need to draw a circle of radius 3 centimeters around A. So you'll get 3 centimeters on your compass, and that'll be like there probably. And then you will draw a circle, if you could do a proper circle, around A, and that tells you that point P, if it's exactly 300 meters from A, it has to be somewhere on this line, because all of these points are exactly 300 meters from A, aren't they? Or 3 centimeters using the scale. Then, so that's that. We know P is somewhere on there. Then it says P is equidistant from B and C. Equidistant from B and C means that if I'm here and you're here, I need all of the places that are exactly the same distance from me as they are from you. So for example, that would be one place, right? Because that's the same distance there as there, roughly. But then so would this, for example. That's the same distance from there as it is from here. So would this. That's the same distance from there as it is from there. So there's quite a lot of places that are equidistant from B and C. So what we have to do here is draw something called a perpendicular bisector. Okay, so I want a line that everywhere on that line, no matter where I am the same distance from C as I am from B. That is called a perpendicular bisector. So what you do is, I mean, you might want to join these up. I think you do want to join these up. It's easier if they're joined up. You need to draw a perpendicular bisector. Okay, a perpendicular bisector is a line that goes through the middle of this line. So that's obviously equidistant from A and B, but also at 90 degrees to it, and then it continues. Okay, so then all of these points would be equidistant from B and C. The way you do that is also similar to what I did before. It requires a compass and some arcs, basically. So this is what you do. You get your sharp point, put it there. Open your compass so that it's more than half of this distance, like up to there, roughly, for example, and draw an arc over here. And then do the same thing from the other side. Put your sharp point there and draw an arc on the other side. So it's going to look something like that initially. Okay. Then open your compass out a little bit further. It doesn't matter, as long as it stays the same the 2 times you do it. Put your sharp point there and draw an arc somewhere here. Right, I don't know how to look, but it'll look like there somewhere. And then do something on the other side as well. So there, roughly. Okay. And then do the same thing from the other point that you got here. Draw an arc. It'll look like there. And then draw an arc and it'll be like there somewhere, roughly. I'm just doing this very, very, very roughly. Okay. But once you've done that, then your perpendicular bisector, or the line that you're after, basically goes from here to here. And it will be roughly like that. Okay. And it'll go on. So if I'm saying that there's a point P, which we don't know, that is equidistant from B and C, it means it can be anywhere on, let's make it a yellow line, anywhere on that yellow line. Because then it's the same distance from B as it is from C, no matter where you are on that line. But also point P was on that red circle, as we said earlier. So if it has to be on the red circle and on the yellow line, then it can only be there or there, surely, because it needs to be on both the yellow line and the red circle. And that basically, I think those 3 examples that I just did One was an angle bisector. One was a perpendicular bisector, that yellow line, and one was just a circle. They are basically the three different scenarios in which you ever have to worry about loci and construction. It's just knowing which ones to do each time, which comes with a little bit of practice. But really, they're the only three examples, and then it's just a case of doing them and practicing them each time. Right, on the basis that nobody's asking me any more questions, I am going to stop and return in 12 minutes to begin going through everything that is on physics paper 1, starting with energy. And I'll do that at 8 o'clock. I have to start at 8 o'clock, unfortunately, because I've got other people who are non-Step Success clients that will be joining it elsewhere. So I have to start at 8 o'clock. So I will be back in 10 minutes.